Hi everyone, welcome to my presentation. Today I would like to talk about a non-invasive technique to measure real-time interface reaction force. First, I would like to thank my advisor, Professor Dev Mishra, and all the co-authors. The question I would like to address first, why this research is necessary. In the United States, every year derailment causes $250 million equivalent property loss. Inadequate track support condition are primary cause for train derailment. Under a wheel load, the magnitude of rail-tie interface reaction force changes with the change of track support condition. Finite element analysis support this statement. A load cell is a conventional way to measure rail-tie interface reaction force in the field, but it requires track modification. In this paper, I will talk about a non-invasive technique to measure rail-tie interface reaction force using strain gauges. The technique relies on the differential shear strain theory. The applied load is related to the induced shear force. To measure rail-tie interface reaction force, two strain gauge circuits were installed. One is called creep circuit, another is called tie circuit. Both two circuits help to measure rail-tie interface reaction force. As the technique heavily relies on strain gauge measurement, the concern is how to calibrate the system in the field and what is the measurement accuracy it will show in the field. To evaluate the objective of this paper, two types of calibration frame were studied to compare the calibration process. Two types of conventional measurement technique were considered to evaluate the accuracy of a strain gauge measurement system. Those are load cell and instrumented tie plate. The details are shown in the figure. The field instrumentation and the test were performed at Letterkenny Yard, Pennsylvania. The figure shows installation process of load cell, instrumented tie plate, strain gauge, and also the data acquisition system. Three types of calibration configuration were studied. For all three cases, the slope of the calibration curve is identical, which means all the three calibration processes will produce similar result. After strain gauge calibration, a static load was applied on top of tie 1 and tie 2 to compare a strain gauge measurement with load cell and instrumented tie plate. At tie 1 location, strain gauge results are very comparable to load cell. At tie 2 location, strain gauge measurements are identical to instrumented tie plate. For dynamic evaluation, a locomotive was run over the instrumented section several times. Similar comparison was performed. A strain gauge measurement showed very comparable result to load cell and instrumented tie plate. The box plot shows the comparison. Finally, based on a static and dynamic evaluation, we conclude that a strain gauge based measurement system is as reliable as a conventional system. I am acknowledging all the collaborators and thank you all for listening.